Welcome everyone to the 2024 Photonics Spectra Summit Series. Thank you so much for attending the Laser Test and Measurement Summit, and in this session you'll hear from Kevin Kirkham, Senior Manager of New Business Development for Ophir at MKS Instruments. Kevin has over 30 years of experience in laser diagnostics and quality assessment, which is why he's joining us today to help viewers better understand the performance of solid-state laser sources. Solid-state light sources. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me, Kevin. We appreciate you taking the time to join us today.
Thanks, Jacob. Hello, my name is Kevin Kirkham. I'm a sales engineer and laser beam profiling specialist with MKS Ophir in Logan, Utah. Today I'll be discussing the measurements of VCSELs and other types of laser diodes. This is an introduction to measurement tools used to evaluate VCSELs, or vertical cavity surface emitting lasers, EELs, or edge emitting lasers, other types of laser diodes, LEDs, waveguides, and solid-state light sources. The goal is to provide a basic introduction into measuring performance parameters of solid-state light sources. It is intended as a basic introduction for those beginning to consider a diagnostic system. Technical light sources are used in hundreds of the devices which our modern life depends. Telecom, proximity sensors, and 3D systems that assess your attention while driving. LiDAR systems that sense our world around us and serve as an aid in imaging, autonomous driving, and virtual and assisted reality. Light sources require individual testing to assure their performance and safety. VCSELs, laser diodes, LEDs, and devices with single and multiple emitters are often assessed automatically by inline test systems. Testing permits manufacturers to eliminate dead and underperforming product and to match devices with appropriate optics or yield profiles. Because of their vertical light emitting structure, VCSELs are often measured in situ. On-wafer testing is commonplace. To confirm performance is adequate for the application, bin for color, intensity, spatial performance, efficiency are all reasons to measure these light sources. The idea is to obtain performance characteristics for further processing, to adjust collimation optics, and to confirm yields. What do we measure? Intensity. Power or energy for a pulse source, or source that may be pulsed in whatever the application or device were used. Pulsing can save battery life if that's what is a concern for the application. We also want to measure spectrum, the center wavelength, and spectral bandwidth, or color where the device is used. Center wavelength, bandwidth, and optical noise changes with temperature. Temporal response. This is the time-based optical output for a given electric input. Important issues include on-off times, overshoot, undershoot, minimum pulse width, and energy efficiency, or energy in for usable energy out. Spatial performance. This indicates how the light propagates or shines out. Spatial performance, or laser mode, is important as it may limit how the light can be effectively applied and dictates how the light should be collected for use. Near-field spatial performance profiling tools and techniques include near-field scanning optical microscopy, or NSOM. NSOM is an optical microscopy technique capable of imaging objects with resolution below the diffraction limit of conventional microscopy, or more commonplace, optical reimaging systems based on a microscope objective for near-field profiling. Far-field profiling is the spatial performance in the far field, or many Rayleigh lengths from the near field. Profiling systems for far field are based on scanning slit, scanning knife edge, and camera-based beam profiling systems. Goniometric radiometers have also been used. One of the acronyms you will hear is LIV. LIV stands for light, current, and voltage. Light-producing devices are measured under varying conditions of electrical drive and temperature. Environmental conditions are important testing, including assessing these parameters over a wide range of temperature and other environmental constraints. So let's talk about intensity. Intensity is typically measured using integrating spheres. Integrating spheres are very useful devices to obtain a sample of the light with a known sample percentage. An integrating sphere is a hollow globe with a spectrally neutral, diffuse coating on the internal surface. Multiple internal reflections from the interior provide a uniform sample. Its function is to evenly distribute the light within the sphere and provide output ports where the light is sampled at a known ratio of the input. These ports provide a convenient way to obtain power, energy, spectral, and temporal measurements. Also used for intensity measurements, large thermopile type laser power detectors. They measure CW power or pulsed energy of the device under test, or DUT. Thermopile laser power sensors with a structured absorbing surface, as in concentric circles, greatly increase the absorption of highly divergent light sources, such as VCSELs. While they are not a substitute for integrating spheres, they are a convenient alternative. Spectrum. Laser spectrometers provide instantaneous information regarding the central wavelength and bandwidth of the light-producing device. Portable, compact, and rugged to large wafer handling systems, there are many types of laser spectrometers suitable for VCSEL measurements. Application of laser spectrometers for testing of solid-state light sources can depend on product test throughput, the format of the device under test, and environmental physical constraints. Temporal measurements. This is how the light source responds to voltage and current. It's called temporal pulse characteristics. Temporal characteristics of the device under test are typically measured with a fast photodiode and an oscilloscope. The temporal oscilloscope trace and measurements such as pulse width, pulse energy, and pulse frequency can be stored with other data regarding individual device performance. Temporal pulse characteristics of the device under test can uncover serious performance deficiencies. Combining data collection. MKS Ophir developed the IS 1.5 VIS-FPD-800 integrating sphere, combining different measurements in a single instrument. Above the schematic diagram of a complete VCSEL characterization system built around this integrating sphere. So the system includes a precision photodiode for calibrated average power measurements, a fast photodiode for pulse shape characterizations on a digitizing oscilloscope, and an SMA fiber output adapter for easy connection to a spectrometer. Spatial light analysis. Beam profiling systems and gynometric radiometers have been used to assess VCSELs in the far field. Now, optical accessories provide methods to obtain near-field and far-field measurements with standard beam profiling cameras. Reimaging systems such as Instrument Systems VTC 2400 and MKS Ophir's Wide Beam Imager, or WBI, reimage the spatial intensity distribution by imaging a diffuser or target screen on which the far-field pattern of the laser is impinged. Ophir's WBI products utilize a special diffuser that has a wide range of acceptance angles. This is so high-angle rays are treated with fidelity. A typical measurement system could include a large format camera, such as this CCD camera, spatial light analysis system where the divergent beam is shown directly onto the camera sensor. Another typical measurement system is where, as I mentioned, the light is impinged on a diffuser or target screen. The spatial analysis of where the divergent beam is impinged, that the image is then relayed by a camera lens to the sensor. Far field is typically imaged in one way or the other. The addition of the basic size and shape, the far field intensity distribution of the beam profile is also useful in determining the divergence angles of the device under test. The far field intensity profile can be acquired with several of these diagnostic tools. However, large format cameras and reimaging devices that measure the far field distribution by intercepting the spherical wavefront with a plane. Planar measurements where the intensity of the curved wavefront is intercepted by a plane is an approach that closely approximates the measurement of the wavefront in the far field. Directly imaging a highly divergent source, such as a VCSEL, or with a CCD or CMOS camera, can underestimate the contribution of the higher angle rays. These are the rays on the edge of the laser's distribution. This distortion, caused by high angle rays being reflected rather than being absorbed by the camera sensor, leads to smaller than actual beam dimensions. Smaller than actual beam widths can cause the calculated divergence angles to also be underestimated. Mode structure, including beam size, beam shape, divergence, and divergence are determined by analyzing the beam profile. Camera-based systems can provide high-speed data collection analysis. Beam profiling applications can be integrated into automated test and measurement environments. These systems provide the spatial performance characteristic of each device under test and permits informed decisions regarding the future of the device. Above, the far field mode is shown. The mode and beam shape changes with drive current. One-dimensional profiles of the spatial beam intensity on the right clearly show how the light output changes with current. Far field divergence is provided in a way to determine the angles that the beam is being separated in the far field. The source is treated as a point source for the purpose of assessing divergence angles. Now, again, the reimaging techniques treat the high angle rays with more fidelity than directly impinging the beam onto a CCD or CMOS camera, where these high angle rays are more apt to be reflected than absorbed and sensed. Near field profiles. Optical accessories that enable camera-based beam profiling in the near field can measure one of many emitters at once. Near field systems may have a field of view of less than 100 microns, so a stable environment and precision motion control is necessary. Aligning the depth of field of the optical magnification system to the near field of the source requires high precision, stability, and micron or submicron control of motion and placement of the device. Here, a camera-based solution utilizing beam profiling software and a microscope objective assesses light as it emerges from the device. With this technique, camera-based systems provide an instantaneous view of the sources in the near-field distribution. This technique is useful for both CW and pulse sources. Integrated systems, such as the MKS Ophir near-field profiling accessory, combine a CMOS camera, adjustable attenuation, and a microscope objective to provide a near-field image for analysis by beam profiling software. Spatial artifacts, including defects, thus a reduction in the overall output intensity of light, are circled in the lower right-hand corner of this near-field image. You can see on the left the actual microscopy image. You can see a slight defect or darkening in the circled device, and on the right you can see a distortion in the spatial distribution of the output of that particular device. Near-field optics permit the capture of the beam profile of a single emitter or many emitters at once. Profiling software enables the measurement of each individual device. Here again, defected emitters are circled. The VCSEL test system varies the voltage and current while capturing and analyzing the near-field distribution of each emitter. Beam profiling applications such as MKS Ophir's beam gauge provide a partition feature where each emitter can independently be assessed for intensity, size, and ellipticity. Conclusions. The many challenges presented in the measurement of VCSELs and other technical light sources can be met with commercial systems or off-the-shelf components. Commercial systems tailored to a specific application may be built from custom systems tailored to a specific application may be built from off-the-shelf components such as mini spectrometers with fiber optic input, integrating spheres with integrated intensity sensors and pulse shape measuring fast photodiodes. Spatial characteristics of the emitted light may be measured with beam profiling applications using cameras and specialized optical accessories that capture the near and far field images and analyze them for size, shape, and divergence properties. A large range of tools are available for diagnostic solution for VCSELs and other technical light sources. Wafer-based systems can offer complete solutions with testing before the sources are diced. Large test and measurement tools provide the, one more time. Try it again, here we go. A large range of tools are available for diagnostic solutions for VCSELs and other technical light sources. Wafer-based systems can offer complete solutions with testing before the sources are diced or cut up. Laser test and measurement tools provide the building blocks for integrated, automated VCSEL test systems. Optical accessories are now available, so beam profiling systems can be used to measure near and far field spatial intensity distributions for assessment of product performance. Thank you for your attention.
Thank you so much, Kevin, for joining us to help viewers master the performance of solid-state light sources. To everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we hope you're enjoying the Laser Test and Measurement Summit. Thank you all so much for joining us.